Welcome to Detectors. Here we're going to talk about the detectors used in gas chromatography. So a mass spectrometer allows for qualitative analysis and can identify a chromatographic peak by comparing its spectrum with a library of spectra. To identify the eluting peak, then two mass spectral peaks can be selected. The quantitation ion can be used for quantitative analysis, and the confirmation ion is used for qualitative identification. That is, the relative abundances of the confirmation ion and the quantitation ion are compared. If the relative abundance is not the expected relative abundance compared to a known sample of the suspected compound, then the compound is misidentified. Another method to identify a chromatographic peak is to compare its retention time with that of a known sample of the suspected compound. And the most reliable way to do this is by spiking, also called co-chromatography. So we spike the unknown sample with a known amount of the suspected compound. And if the chromatographic peak is due to the same compound as that added compound, then the relative area of that chromatographic peak will increase. And this procedure should be carried out on multiple columns with different stationary phases to ensure that the identification is in fact correct. Because if that peak is growing on multiple columns with different stationary phases, then we can be reasonably sure that we don't have two separate compounds that simply have the same retention time on the column that we've been looking at. Quantitative analysis of a chromatographic peak is based on the area of that peak, not on the height of that peak alone. In the linear response concentration range, the area of the peak is proportional to the quantity of that component. In most instruments, the computer reports the peak area for us. If you have to measure the peak area by hand, and the peak is Gaussian, then the area is equal to 1.064 times the peak height times W1/2, where W1/2 is a full width at half max. In the days of paper chart recorders, the peak area could be measured simply by cutting out the peak with a pair of scissors and weighing the scraps of paper that contained that peak. Quantitative analysis is usually performed by adding a known quantity of internal standard to our unknown, and see section 5.4 for more details on internal standards. So this brings us now to specific detectors, and the first one we're going to talk about is the thermal conductivity detector, or the TCD. Now, thermal conductivity detectors used to be quite common because they are simple and they respond to all analytes. The TCDs are useful for packed columns, but their low sensitivity makes them less useful for open tubular columns or capillary columns. A thermal conductivity detector consists of a hot filament here in blue, surrounded by a cavity that's kept at a constant temperature. And the carrier gas used with TCDs is normally helium. Helium has the second highest thermal conductivity. Hydrogen has a higher thermal conductivity. And so as the helium flows in here and past our filament, this is usually a tungsten-rhenium filament, it then carries away some heat from our filament. And as the analyte enters the detector, the thermal conductivity of the gas surrounding that filament, so the helium plus the analyte, decreases. That is, the thermal conductivity of the mixture will be lower than that for the helium alone, unless the analyte is hydrogen, because helium has the second highest thermal conductivity out of all substances, with the highest being hydrogen. So as long as our analyte isn't hydrogen, then whatever else we mix in there has a lower thermal conductivity than helium does, and that means that mixing it in with the helium will lower the thermal conductivity of the mixture. And as the thermal conductivity of the gas surrounding the filament decreases, the filament temperature increases. And as the filament temperature increases, its electrical resistance increases. And this means that the voltage required to pass a constant current through that filament, therefore, increases. And this voltage drop across the filament is then measured by our detector. So commonly, the carrier gas is split into two streams, with one going through the analytical column and one going through a matched reference column. And the voltage drop across the sample filament is then compared to the voltage drop across the reference filament. And this procedure minimizes the flow differences when the column temperature is changed. The sensitivity of the thermal conductivity detector increases with the square of the filament current. However, that maximum recommended current should not be exceeded, or the filament lifetime will be significantly reduced. Furthermore, the filament should be off if the carrier gas is not flowing past it. We don't want any oxygen there while that filament is hot. Also, the sensitivity of the detector is inversely proportional to the flow rate. That is more sensitive at lower flow rates. And the sensitivity also increases when the temperature difference between the filament and the surrounding block increases. And that surrounding block, the detector cavity, should thus be kept at the minimum temperature at which all the solutes will remain gaseous. Now let's look at a different detector, the flame ionization detector. In a flame ionization detector, or FID, the eluate is burned in a mixture of hydrogen and air. Now, carbon atoms, other than carbonyl and carboxyl carbons, produce CH radicals, which then produce CHO plus ions and electrons in our flame through a process like this. So we've got here our air inlet, our gas is flowing in from the column, we're burning it here in our flame, and then up here we have a collector. So while only a small fraction, so maybe 1 in 10 to the 5th, so 1 in 100,000 carbon atoms produces an ion, the ion production is proportional to the number of susceptible carbon atoms entering the flame. And the electrons then produced in the flame are collected by the positive electrode. This is the collector up here, which is held at around 200 to 300 volts with respect to the flame tip there. Now, in the absence of analyte, the current between the flame tip and the collector is around 10 to the minus 14 amps. But when analyte is present, then the current between the flame tip and the collector is around 10 to the minus 12 amps. And this current signal is then converted to a voltage, amplified, filtered to remove the high frequency noise, and converted to a digital signal that's then passed on to our computer. The detector response to organic compounds is proportional to the solute mass over 7 orders of magnitude. The detection limit is 2 orders of magnitude lower than that for the thermal conductivity detector. And the detection limit can be improved further by using nitrogen instead of helium as a carrier gas. Now, the flame ionization detector is sensitive to most hydrocarbons, but insensitive to non-hydrocarbons, including hydrogen gas, helium gas, nitrogen, oxygen, carbon monoxide, carbon dioxide, water, ammonia, NO, hydrogen sulfide, and silicon tetrafluoride. The thermal conductivity detector responds to all analytes. The flame ionization detector responds to most hydrocarbons, but most of the other detectors that we're going to look at only respond to certain classes of analytes. For example, the electron capture detector is quite sensitive to molecules containing halogens, conjugated carbonyls, nitriles, nitro compounds, and organic metallic compounds. It's relatively insensitive to hydrocarbons, alcohols, and ketones. And the carrier gas must be either nitrogen or 5% methane in argon. And we have a cavity here that is lined here and there with nickel-63 that emits beta particles. And these high-energy electrons then ionize gas in our detector here, and those electrons in the plasma are then attracted to the anode here. Now, the current between the cathode and the anode is kept constant using variable frequency pulses that are applied between the anode and the cathode. And when an analyte with high electron affinity then enters the detector here, it captures some of those electrons in the plasma, thereby decreasing the conductivity of the plasma. And the detector responds by varying the frequency of voltage pulses in order to keep the current constant. And the frequency of the pulses is then the detector signal. So the electron capture detector is extremely sensitive. The detection limit is comparable to that in mass spectrometric selected ion monitoring. The nitrogen-phosphorus detector, or alkali flame detector, is a flame ionization detector that is modified to be more sensitive to compounds containing nitrogen and phosphorus. The response to nitrogen and phosphorus is 10 to the 4 to 10 to the 6 times greater than the response to carbon. And the detector has a glass bead containing rubidium sulfate at the burner tip. Now, ions such as NO2-, cyanide, and PO2- are produced when those elements contact the bead and carry the current that is measured. And note that rubidium sulfate is consumed in these reactions, and thus the bead must be periodically replaced. And note that N2 is inert in the detector and is thus not measured, so it can still be used as a carrier gas. A flame photometric detector measures the optical emission from phosphorus, sulfur, lead, tin, or other selected elements. The detector is similar in construction to the flame ionization detector that we've already talked about, and when LU8 passes through a hydrogen-air flame, the excited atoms emit light at characteristic wavelengths. Those wavelengths are characteristic of whatever elements are in that flame. A photoionization detector uses a vacuum ultraviolet source to ionize aromatic and unsaturated hydrocarbons. Electrons produced by the ionization are then collected and measured, similar to the flame ionization detector. The photoionization detector is insensitive to saturated hydrocarbons and halocarbons. A sulfur chemiluminescence detector takes the exhaust from a flame ionization detector in which sulfur has been oxidized to SO and mixes it with ozone, so O3, to form an excited state of SO2 that emits light in the UV and in the visible, in the blue region here. The emission intensity is proportional to the mass of sulfur eluted, regardless of the source. And the response to sulfur is 10 to the 7 times greater than the response to carbon. Similarly, a nitrogen chemiluminescence detector is similar to our sulfur chemiluminescence detector. Combustion of the LU8 at around 1800 degrees C converts nitrogen into NO, which then reacts with ozone to form a product that luminesces. The response due to nitrogen is 10 to the 7 times greater than the response to carbon. So we can also couple gas chromatography with mass spectrometry. And selected ion monitoring and selected reaction monitoring can be quite helpful in identifying chromatographic peaks. Now, see Chapter 21 for a discussion of mass spectrometry, including these selected ion monitoring and selected reaction monitoring techniques. We can pass the LU8 from the column through a plasma to atomize and ionize its components and measure selected elements using atomic emission spectroscopy. And note that this is similar to the inductively coupled plasma atomic emission spectrometers that were discussed in Chapter 20. Sensitivity for sulfur can be 10 times better than the sensitivity of a flame photometric detector. And that was Detectors.